Okay, in the last section, we learned that when two events are independent, the occurrence of one event has no effect on the probability of the second event. But we cannot always assume that two events will be independent. Will the probability of being in a car while driving on a dry road or an icy road have the same likelihood of an accident? Okay, probably not. This is called conditional probability. So conditional probability. And here's our notation for it, and it's read the probability of F given E. Oh, here we are. Okay, it's the probability that F occurs given that event E has occurred. Okay, so here's an example. Suppose that a single six-sided die is rolled. What's the probability that the die comes up 4? Now suppose that the die is rolled a second time, but we are told the outcome will be an even number. Then what's the probability that the die comes up a 4? Okay, so let's look at our sample space for each one and see if we can calculate the probabilities. So for the first one, our sample space it's just what's the probability a die comes up 4. So our choices are 1, 2, 3, 4, 5, 6. So there's 1, 4. So the probability that we get a 4 is 1 out of 6. But now let's look at the second question. And it says, what's the probability that we're going to get a 4 if we know it's an even number to start with? So given that it's an even number, that means our only choices to get the 4 are 2, 4, and 6. So probability it's a 4 given that you know it's even is just 1 out of 3. Okay, totally different. This is called a conditional probability, right? Because you know some condition beforehand. Okay, here's our conditional probability rule. Okay, if E and F are any two events, then the probability of F given E is we find the probability that E and F occur at the same time divided by the probability that E occurs. Now, since these are going to be fractions, we can simplify that to one fraction instead of we don't want a fraction over a fraction. And so we could do the algebra to simplify that, or we could just simplify our formula and say, oh, it's the number of occurrences of E and F, right, divided by the number of occurrences of just E. Okay, let's see an example of that. Okay, so a survey was conducted by the Gallup organization, conducted May 8th through 11th in 2008, in which 1,017 adult Americans were asked, which of the following statements comes closest to your belief about God? You believe in God? You don't believe in God, but you do believe in a universal spirit or higher power, or you don't believe in either. So the result of the survey by region of the country are given in the table. Okay, East, Midwest, South, West, and I believe we're going to continue on the next slide. I'll keep this data on the next slide, but here's our question. Okay, so what is the probability that a randomly selected adult American who lives in the East believes in God? Okay, so this is the probability that you believe in God given that you live in the East, right? Because it says a randomly selected American who lives in the East. So we're given that. We know he lives in the East. What's the probability that he believes in God? All right, so I need to come up here and I need to find the number. Let's write it out like this for us one time, right? Of outcomes of people that live in God, that believe in God and live in the East. 204. Divided by the number of people that live in the East. Oh, well, here I've got to add this up. So 204 plus 36, 204, 255, right? So I need this total. Okay, don't forget to double check and see if that will simplify. Always double check. And our calculator tells us that is 4/5. Okay, now this one is, what's the probability that a randomly selected adult American who who believes in God excuse me, lives in the East? So this time we're we are given the fact that the person believes in God. So what's the probability that he lives in the East, given that he believes in God? What's the probability that a person that believes in God, that's what we're given, lives in the East? So this is still the number that lives in the East and believes in God, but now it's got to be divided by the number that believe in God. Okay, so that's still 204, but now I need to add this up. Okay, so let's see what that is. 204 plus 212 plus 219 plus 152. That's 787. So let's see if that'll simplify. 204 divided by 787. Does not simplify. Okay. Makes sense? Let's see what else we have. Okay, in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What's the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24 years old? Okay, so what's the probability that the person was male, given that he's 20 to 24 years old? So we need the number that's male and 20 to 24 years old divided by the number that's 20 to 24 years old. Okay, so male and 20 to 24 years old. And there were 16.6 of all murder victims were 20 to 24-year-old males. So 0.166 over, just how many were 20 to 24? 0.191. Or Okay, 0.869. Okay, notice it doesn't matter the order you put these in because it's an and. You know, A and B, B and A, same number. But what I have to be careful of is what goes down here, right? Okay, and this number that goes on the bottom is what you're given. Okay, the probability that two events, E and F, both occur, here's another formula for us, okay? And notice that if they were independent, we just multiplied the two individual events. But if they're not independent, then we do the probability of E times, not just the probability of F, but the probability of F given E. Okay? So here's an example. Oh, it's the same thing. In 2005, 19.1 of all murder victims were between the ages of 20 and 24. Also in 2005, 86.9% of murder victims were male, given that the victim was 20 to 24. What they do, give us a different year because that's a different number. Okay, what's the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? Okay, so it doesn't tell me about given anything. Oh yeah, that's why we have a different year here. Okay, so we're going to need, okay, so this is going to be, we want to know what's the probability that the person is 20 to 24 and male, right? That's what this means, that he's 20 to 24-year-old male. Oh, it means he's 20 to 24 years old and he's a male. That means I need to find the probability that he's 20 to 24 years old, and then I'm going to multiply it by the probability that he's 20 to 24 years old, given that, well, let's know. Sorry. That he's a male, given that he's 20 to 24 years old. Okay? So let's see. The probability that he's 20 to 24 years old, okay, also in 2005, were male, given that the victim was 20 to 24 years old. Okay, so 19.1% of all murder victims between the ages of 20 and 24 years old was 0.191. And in 2005, 86.9% were male, given that they were 20 to 24 years old. So I'm just going to multiply these two. Where'd it go? 869. Which is and that's a number we just found, right? It's still in my calculator. 0.166. Okay, just plugging into a formula. Okay, what about this one? Suppose that a single card is drawn from a standard 52 card deck. What's the probability that the card will be a king? Okay, so the probability that you get a king, there are 4 kings and there's 52 cards. So that's 1 out of 13. Now suppose that a single card is drawn from a standard 52 card deck, but we're told that the king is a heart. What's the probability that the card drawn is a king? So we want to know what's the probability that we have a king given that it's a heart. Okay, so this is the number of cards that's kings and hearts out of the number of cards that's hearts. Okay, did the knowledge that the card is a heart change the probability that the card was a king? No. What term is used to describe this result? Independence. Right? Independence. If the effect of event E has no effect on this, they are independent, right? Okay, suppose that 2 cards are randomly selected from a standard 52 card deck. Okay, what's the probability that the first card is a king and the second card is a king if the sampling is done without replacement? Notice this one says with replacement. Okay, so what that means is you take a deck, you shuffle it up, you draw a card, you look at it. Without replacement means then you draw another card and look at it. Now, with replacement means after you look at the first card, you put it back in the deck, you shuffle it, and you draw a card. The difference between these two is that one of them is independent and one of them is not independent, right? This one is independent because if you look at that card, then you put it back in, shuffle, draw, your probability of drawing your next card's exactly the same. But this one is not independent because if you hold a card out, for one thing, you're no longer drawing from 52 cards, and there's no longer 4 kings in there. Remember, we're assuming doing these probabilities, the probability of E given F, we're given that first occurrence occurred, that first probability actually occurred. So this says, I want to know what's the probability that I draw a king and another king, but without replacement. So the probability I draw that first king is 4 out of 52. Okay, but now that second king, since I'm holding that king out, there's only 3 kings left and 51 cards left. So 12 out of 2,652. Okay, and that will reduce to 1 out of 221. Okay, now, same thing except with replacement. What's the probability you draw a king? You put it back in and draw another king. 4 out of 52 times 4 out of 52 because they're independent, right? This draw was not affected by that draw. So I know that's 1 out of 13 times 1 out of 13, or 1 out of 169. Okay. Let's look at one more. Okay. Suppose that a poll is being conducted in the village of Lamont. The pollster identifies her target population as all residents of Lamont 18 years or older, and this population has 6,494 people. Compute the probability that the first resident selected is Rick Smith. Let me get my pen. That the first resident selected is Rick Smith and the second is Roger Black. Okay, well, Rick Smith is one person out of 6,494. Okay, and the second one, Roger Black is one person, but now that I've taken Rick Smith out, there's only 6,493 people. So that's 1 over 6494 times 6493. So 42,165,542. Let's see what that is as a decimal approximation. Okay, so 7 zeros. And then 237. Okay, now let's compute the probability that Rick is selected first. So the probability that Rick is selected first and Roger is selected second, but we're going to assume that they're independent, that one doesn't affect the outcome of the other. So this is still 1 out of 6494, but if they're independent, this is also 1 out of 6494. So this is 1 out of 42,172,036. Let's do a decimal approximation. Okay, 8 zeros. 2, 3, 7. Right? So on this one, if we'd have expanded it out, I'd have 2, 3, 7, 3, 8, 5. This one, 2, 3, 7, 1, 2, 3. But these numbers are close enough to identical, right? We don't get a change until the 12th decimal place. So our point is, when small samples are taken from large populations, even if it's without replacement, we can assume independence, right? So that's going to be important later, that we can assume independence. Okay, so this answer, just as good as this exact answer. As a matter of fact, they appear to be nearly exactly the same. Okay, this is going to be an important idea. All right, let me know if you need anything.